tombstone, skyscraping. All the rock stars double dating. So if you hate me, go on hating. You've been waiting your whole life for this moment to be waiting. In their fucking cars, 12-stepping hippies hanging out at the bar. Suckers and fuckers and stupid retards. New York City's like a graveyard. City's like singing on the prairie. New York City's like a cemetery.
Alright, so today we're going to continue and do some more exercises on loops. I've got 2 pre-prepared exercises here, but we can always pull out more. Before we do that though, remember that this week is the career fair. It starts today and goes through Thursday, and even though they advertise 1 or 2 of those days as the computing days, really you should go to all of them, because one year I went just to see who's there. There were maybe that was the engineering day, and they had a construction engineering, right? They had like a dozen firms that do construction engineering, and they weren't looking for construction engineers or mechanical engineers. They were looking for computer science software developers. So you can everybody needs programmers. Everybody needs software developers. So you should be going to all 4 of those days if you can make it. All right. Remember that if you dress up, I think you get free headshots. Have your resume, maybe a generic cover letter, just to hand out to folks. Even if you're not looking for something right now, right? They're gonna have that stuff in their records, and they're gonna be contacting you. So make sure that you're taking full advantage of those. And then remember, next week we've got our own mini career fair just for computing. I think that's the 24th, but don't quote me. But that's going to be in the Shore Center one of those nights. Then also upcoming here is not this week, but next week, Friday, is your first exam. Just to give you a preview of that, it's going to be an executable exam. We'll release it at 1 second after midnight that Friday morning. You will have until midnight of that Friday evening to complete it. It's only designed for 1 hour, right? And you complete it anywhere you want. We're not going to have a physical class that day. You do it wherever you want, just no collaboration with anybody, no usage of tools, AI tools or anything like that. You submit it to CodePost. You can submit it as many times as you want, just like your hacks and your labs, and it will auto-grade and give you the score right there. So that is next week. Next week is also your fix-it week. So if you messed up one of your hacks or you messed up one of your labs, you'll be able to resubmit it that week, one of them, all right, one of each, and you'll be able to submit it that week for full credit and full points to earn those back. Yeah?
Is the exam in C and Java?
Yeah, well, so There are only 2 exercises, your choice. You do one in C, you do the other in Java, whichever one you want. You don't have to do 4 exercises, but once you've done one, we're still in the simple enough phase that once you've done one, then you can easily translate it. Another question? No?
No.
Oh, okay. Yeah.
What's the venue for the career fair?
It's usually in the union, I think, right? Yeah? Okay. Somewhere in the union, probably multiple places in the union because it's that big. Okay. All right, so our second exercise, dealing with loops, is to compute a loan amortization table. So you might not have taken out a loan in your life yet, but maybe someday you will. But if you take out a loan for, say, $10,000 to buy a used car, a cheap used car, and you do it over a period of 5 years, you're going to have monthly payments. So 5 years, 12 months in a year, that's going to be 60 payments total. And they're going to be charging you interest because that's what banks do. Right? And so based on those 3 inputs there, your monthly payment is going to come out to the rate, which is a monthly rate, because they don't charge you that entire year's 5% in 1 month. You divide it by 12, multiplied by the principal, and then 1 minus 1 or plus the rate raised to the negative end here, right? That gives you a payment of $188.71. Now that's going to be rounded because you're not going to be able to pay fractions of a cent. So that ends up getting rounded up or down, whichever the case may be. And then you start paying that monthly. Now, each month, you're not paying all of that to your principal. There is a certain amount that gets paid towards the interest, and then the remainder of that $188.71, that goes to the balance, paying down that loan each month. So you can see over time here, the amount that you're paying to interest goes down. That's why it's called amortization. You're looking at the entire life of the loan. You're not actually paying 5%. You're paying slightly less than 5%. Right? And this is calculated by taking the balance, multiplying it by the monthly rate. If I were to go 5% divided by 12, right, then that comes out to about $41.67 when it's rounded. Right? Let's go ahead and go to Wolfram Alpha here. And 5%, 0.05, divided by 12 times 10,000. In that first month, you're going to be paying $41.66666666. But rounded to the nearest cent, that's only $41.67. $188.71 minus the amount that you pay towards your interest, that gets applied to the balance. That gives you a new balance. The next month, that new balance is what is used to calculate that interest. So instead of $10,000, you're going to be paying $9,852.96, right? You're going to end up paying that much in interest instead. $41.05 rounded down again gives you $41.05. And then the amount that you're paying towards the principal goes up. Okay? So now that we understand how loans work, let's go ahead and compute this loan amortization table for any balance or any principal that you borrow over any number of years at an annual fixed interest rate right there. Okay? Once again, I'll let you choose C or Java on this. Java? We did Java last time though. We can say what? Well, no. We could do it in Python if you want to. Yeah, so do we? Which we can do either one. Java. All right, we're already here. Let me go ahead and if you want to see the C version, you can watch the main video, the main sections video from Friday if you're really interested. But otherwise, let's go ahead and just go with loan. I'll call it loan. And let's just go ahead and put this into public static void main string args. Because both of these exercises that we're going to do today are good segues into the next topic, which will be mostly after the first exam, but functions. We're not expecting functions on, but if you want to write functions for your hack this week, for your exam one, that's perfectly fine, right? But we're not going to grade based on that. All right, so I'm just going to go ahead and fix these values for this one test case right here, right? This one, and then what we can do later on is we can, read these in as command line arguments instead. So I'm going to obviously need 3 variables here. The principal that you borrow, which was $10,000. Oops. Right. The Number of years, right? 5-year loan, 6-year loan, 7-year loan. Right? You can go fractions on that, but it's not usual. So what kind of variable would you use for that 5-year loan? Int, num years, right? Years, whatever you want, 5. Hard code that to 5 for now. And then 5% interest rate. That is going to be a double. In fact, annual interest rate. And I'll say that that's 0.05. That's 5%. It's not the whole number 5 is 5%. If you want it on a 0 to 100 scale, you can do that. It's just that for all of our calculations, we're going to have to divide by 100 then. Okay? The first thing to do is get a hold of this monthly payment and make sure that it's correct. That's going to be the rate, but be careful, that's the monthly rate, right? That's 5%, the annual rate divided by 12. So that kind of tells me maybe I want yet another variable, right? You're not paying by the variable, you might as well create one. Monthly rate is going to be equal to the annual interest rate, or annual rate, right, divided by 12. Is there going to be an integer truncation issue here?
No.
No, because this guy is a double, right? Now that I've got monthly rate and annual interest rate that's kind of inconsistent, I like shorter variable names when it's clear. So let's go ahead and rename this one immediately. I want to do this so that I can show you a trick. If you have a variable that permeates throughout your code and appears 100 times and you want to rename it, don't go copy, paste, copy, paste, copy, paste. Instead, right click, refactor, rename, and it'll be annual rate. There we go. And it changes everywhere for you automatically in the IDE. VS Code also supports this, but I don't remember how to do it off the top of my head.
The option is called rename symbol.
Rename symbol? Okay. Is there a right click on it or something? Okay, right click, rename symbol. Right. Okay. All right, I've got my monthly rate. Now let's go ahead and go with monthly payment. I'm not going to call it P, am I? No, because that's not descriptive. That's perfectly fine over here in the finance or mathematical world or formula world, right? Where they want to shorten everything. So instead, what I'm going to do is I'm going to say double monthly payment. Right? And I'm going to transcribe that formula right there. It's going to be the monthly rate times the principal in the numerator, and then something in the denominator. Right? That something in the denominator is going to be 1 minus 1 plus the monthly rate raised to the power negative n. Couple problems there though, right? First of all, do I have n? What was n standing for? Is the number of total periods, months in the loan. So what I could do is I could inline this and go years times months, or I could create yet another variable. Int num terms is much more descriptive than n, right? Num months if you want to, or months if you want to. I'll say that this is going to be num years, and we all know that there are 12 months in a year and they ain't making more. Right? So now this is going to be num terms. Right? Still a problem here though. Can we do this? No. There is a meaning to that. It's a bitwise exclusive OR operator in both languages, but it doesn't get you what you want. It doesn't raise something to a power. How do we do that in Java? Math.pow, right? And I will raise that to the power negative num terms. And now I need to balance my parentheses. Right? Long line, you can break that up if you really want to. Go ahead and break that up into the next line. If you reformat this, of course, it's going to want to make that long line. Whatever you want to do to make this a little bit more readable. I want to know if that was correct. Right? So you can do the poor man's way of system.out.println of monthly payment. This is poor man's debugging, right? Where you can't afford a real debugger, and you just print something and then you move on, you print something, you delete this because, okay, now I know that that's okay, and then you go back and no, now it's not okay, and I need to restore that print statement, et cetera, right? Or what you could do is you could start using a proper debugger. This is something that we're going to cover in depth later on. What I just did is I double-clicked over to the side here on line 13. That sets what's called a breakpoint. And instead of hitting play, I can come up here to this little bug instead, which will run the program. Oh, come on, what's wrong? Save it, run the program. Okay, there we go. I don't know what was wrong. Let's go ahead and switch to my debugging perspective here. And you see all the values over here. There's the principal, 10,000. There's the number of years, right? There's the number of terms, 60. You can highlight each one of these. Now what it's done is it's executed this program up until line 13. I'm going to go now to the next line by stepping over that. And you'll see that, the next line, there we go. And is monthly payment up there yet? Nope. So step over, there we go. Monthly payment now appears over here. I don't have to print it out, right? All I have to do is examine it in my debugger, okay? And there's a whole bunch of other things that you can do with the debugger, and we'll cover that in more depth later on, but you can start using it right now to not have to print things out just to see if they're correct. Now, is that correct? 18871 and then fractions of a cent? Careful. Are we going to be able to pay fractions of a cent? Give me a half a penny. Can you? Nope. A halfpenny or whatever the English call it. All right, and I'm going to go ahead and terminate this and go back to my Java perspective over here. You see now you have a new perspective up here, the debugging perspective that you can go back and forth on. Right? So what do I need to do to my monthly payment in order to make it $188.71 exactly? I need to round it. So monthly payment is equal to math.round monthly payment. Yeah, I need to round it not to the nearest whole number, but to the nearest 100th, the nearest cent. So once again, it was $188.71 and then 23 whatever. I need to round it not to here. I need to round it to here on my cursor. What if I moved this period over here and then called the round function? Would it work? Yep. But then it wouldn't be the correct value. You're not paying $18,000. So what do I need to do to correct it? Move it back over. And like you said, it's a multiplication by 100 and a division by 100. You don't need to go 0.0 because there's no truncation issue there, right? But I'm going to do it just to be clear. I'm probably going to be doing this multiple times because I've got this entire table to generate over here. If you're going to be doing something multiple times, right, not in a loop, but the same operation in different parts of the code, that should be your signal that I need to take that code and put it into a function so that I can reuse that function. I don't have a round to cents function in the math library, right? Because that would localize it entirely to United States code. Only U.S. code would work in U.S. dollars, right? There are plenty of other currencies out there, and so rounding, where would you want to round it to? Sometimes you don't want to round it, etc. And so they didn't put that into the math library. Possibly there's one in the currency library, but I don't want to go that far. So what we could do is we could immediately up here start doing the next topic and create a public static double round 2 cents that takes a value x, right, or a currency value, and simply returns math.round x times 100 divided by 100. The same trick that we developed down here. And now what I can do is instead of calling this math.round is I can call that round 2 cents. Right? I'm not going to multiply by 100 and divide by 100 anymore. Why? Because the function is doing it for me. Again, we're not expecting this until week 5 or after your first exam. But if you do start doing this, then you need to start documenting all of your functions. Right? And to do that, you use doc style comments. Rounds the given value, or not the given value, but returns the given value rounded to the nearest cent, that is 100th spot. right? Whatever, however you want to document it, right? Returns the given value rounded to the nearest cent. That's all you need. Right? That's what it does. I mean, a good function name would do that for you, but you still need documentation on all of your functions. Okay. All right. I'm more or less convinced that that will work. We now need to work on generating this table. I'll leave it to you to generate this header and get it just right and pretty if you want to. What I want to do is I want to work on this. In the first month, we're going to have to calculate, well, we've already got the balance, right? The balance is going to be the principal initially. And then we want to compute the monthly interest rate, or the monthly interest period, not the rate. And then the remainder that goes to the balance. And then finally the new balance over here. Right? Let's just do it for the first month here. Right? So my month is going to be the first month, double. The interest, or month's interest, is going month interest is going to be equal to, all we're doing is taking this monthly rate and multiplying it by the current balance. All right, so monthly rate times the balance. Because the balance is going to change. The principal doesn't change. You borrowed $10,000, right? You pay that down, that's called your balance. So we also need another variable over here, balance. That's initially going to be the principal. Right? You could get away with fewer variables if you wanted to, but make more variables, right? It's more expressive that way. There's the month interest. How much is going to the principal? Month principal is equal to the monthly payment minus what you put towards the interest. All right. Now, before we print these out, do you see any future problems here? Same problem as up here. Your monthly payment is not needed to be rounded to the nearest cent. What else needs to be rounded to the nearest cent? Balance. We'll assume that they gave it. We'll assume that they didn't say that they wanted to borrow $10,000, 23 cents, and a fourth of a cent. We'll just we could do input validation up front. So the balance, as long as whatever you're taking off of the balance is rounded, then the balance that should be rounded too. So double new balance is going to be the old balance minus your monthly principal payment. All right. We could go ahead and get overly aggressive and just go ahead and round all of these things if you want to, right? But probably the only one that actually needed to be rounded is the monthly interest. Because if you already rounded the monthly payment, right, and the monthly interest is now rounded, then of course the monthly principal is going to be rounded. I don't know why I don't have enough real estate. There we go. All right. Let's print those things out. System.out.printf. The month is going to be a integer. Right? Then we're going to have some dollars here, so that's out to 2 decimals places of accuracy there. Percent to f, sorry. In fact, we're going to have 3 of those, right? 4 of those, sorry. 1, 2, 3, 4. Right? So here it's going to be the balance, the monthly interest that we paid, monthly principal that we paid, and then finally the new balance. Let's see if that works for the first iteration here. Oops, what's wrong? Oh, the month, thank you. Month. All right. 10,000, 4167, 14704, is that right? Yep. And then 985296. Okay. Do that again. All of this stuff gets updated, but with the new balance instead. Right? We could go ahead and copy and paste this and do this like 3 times and verify that all our calculations are correct. But you know what? Let's just go ahead and immediately write a loop to do this. Do you know how many times this loop is going to execute? Oh, careful. If we take it out at 5 years, are they going to spring? Oh, nope, sorry, you got now 6 years of payments. If you didn't pay, of course, then yeah, right? 60 in this case, which we put into num terms. Where was that? Right there. Okay. So instead of creating month, well, I could do this. Int for int month equals initially 1. Month is less than or equal to the num terms, month plus plus. That gets rid of this variable. And there. Let's see if that does it for 60 months. Right? Oh, okay. That works, but it's not pretty. Let's go ahead and end the line there. There we go. So I see 60 months here. Cool. Right? But I don't see anything changing. Yep. So balance is only equal to the principal when? At the beginning, right? Before you start this loop. Now once I've got this new balance, what I can say is the balance after you paid it is the new balance. What if I'd done that up here instead? Yeah, it'd change it to what? Well, first of all, I don't have new balance here yet, all right? Right? But it would be off by 1. You'd be prepaying by 1 month or something like that, right? All right, so let's check that out. 9852, let's go ahead and bring this over here and decrease it. 985296, and then 30 cents, 3 cents, 14 cents. Yeah. This ellipse here is just because I didn't want to print out all 60 months over here. All right. And what would you expect at the end of the loan? You don't, yeah, you don't owe anything, right? That's always going to happen because of rounding, right? So I'm going to put in a to-do here. You may need to handle the final month separately. Because with loops, you're always, there are problems where you're always going to be off by 1. Either that first initial iteration is going to be different from all the others, or that last one is going to be different from all the one previous to it, or both, or something like that. And in this case, that's how loans work, because you can't pay fractions of a cent. At the end, you might owe this little tiny amount. And so your last monthly payment would be $188.21. However, in the real world, I think that if your loan balance falls below like $1 or something, then they just wipe it out and you don't actually owe anything, right? Just for convenience.
Do you wipe it out sooner or later?
It depends on, we didn't say what was up here, right? So you'd go back to your stakeholder requirement solicitation and say, what happens at the end of the month? What are the financial rules, right? Because I just said, all right, we're going to round to cents. Right? I don't think that that's actually what happens in finance, right? They want their fractions of a cent or something like that. I don't know how that works, but there are rules for it that have been established by either the government or other entities, right? So that's good enough for now. Putting in your to-do here means I'm going to take care of it later. How would you take care of that later? You wouldn't go up to and including that last month, would you? You'd go with that, right? And I'll leave that to do in there, but because you'd be off by 1. All right. All right. Here's our last exercise. Write a program that, given an integer n, calculates the number of primes, 2 to n. So 2 is a prime, 3 is a prime, 4 is not a prime because it's divisible by 2, 5 is a prime, 7 is a prime, right? So if I gave you, say, 10 here, it would be 2, 3, 5, 7, 8, 9. That's it. 4 is what we would want. Right? So, where do you want to start here? C or Java? C? Okay. C. Num primes. Let's see. And let's go ahead and demo. I'll grab all of this stuff over here and put it over here. There we go. Okay. Again, documentation. This program computes the number of primes from 1 to n inclusive. Right?
Could be 2 to n.
Okay, well, yeah, same thing, because one's not a prime or a composite. It's something else entirely. All right. All right, once again, let's just go ahead and hard code this for a second. And let's say that 100, because that's pretty easy enough. You can pull out a table of primes, or you can ask, Wolfram alpha, how many primes are there? Number of primes 1 to 100. Right? And we should get that, well, it's going to list them all out there for us, but how many are there? 20, where did you see that? 25 integers. There we go. So if we go ahead and hard code this to 100, ultimately we've got the expected output should be 25. Right? So I want to test everything. Right? We'll be naive about it up front here. For int I equals 2, I is less than or equal to n, I plus plus. I want to determine if I is prime or not. Right? And if you want to, you can rename this as x or something. Right? Because it's no longer an index variable or an increment variable. It's the actual variable x that you want to determine if it's prime or not. Right? So how do we do that? Grade school method, right? Or this is also called the kind of, it's not exactly, but the sieve of Eratosthenes. You just try everything. If I gave you 57, is that prime or not?
It's not.
No, divisible by 3. Let's go with 59 then. Now, how do you test for this?
Go through every single number.
Yep. Is it divisible by 2? Nope. Is it divisible by 3? Nope. Is it divisible by 4? Nope. Is it divisible by 5? Nope. Right? So all I'm going to do is for each potential divisor 2 up to some value here, right? Test if x is divisible by, and I'll call it d, right? By d. There. Right? So let's write that loop. For int d starting at 2, d is less than that question mark that I had, d plus plus. This is very naive, right? Of course, you never need to test any even numbers other than 2, right? And so you could go test 2 and then test 3 and then only ever go up by 2s, 5, 7, 9, etc., etc. In fact, once you know that something is, actually we won't get into the actual sieve of Eratosthenes. Let's just go ahead and do it the naive way here. Right? But do I have to test everything up to and including n? No. If something is divisible by something like 2, 3, whatever, if think of it on the number line here, 2 up to n. Right? We're looking at a divisor right here, whatever d happens to be. If d divides n, what else divides it? Something over here, right, on the other side of this not exact midpoint, but something right here. Right? So what is that something? You could say that, well, just take the average here, right? And then that is the true midpoint, because if something divides it over here, then certainly something divides it over here. But I'm thinking of something else even smaller. So what if it's divisible by, if it's divisible by 2, then that means that there's something over here, n divided by 2, right? If it's divisible by 3, then you have something over here, n divided by 3. When do I meet it in the middle? When it only has two divisors. Right? At y times y is equal to n. What is y? Square root of n. You only need to go up that far. Right? And you need to include it though, because it could be a perfect square, right? 3 is a, 9 is a perfect square, 3 times 3, right? So I only need to go up to square root of n. But I do need to include it, right? So if d, or how do I test if x is divisible by 3? Mod d is equal to 0, right? Then let's even print it out. Printf percent d is divisible by Oh, sorry. Yes, I said n over there. Right? Maybe that was the confusion. I switched to n up there. Yeah, sorry. Is divisible by percent %d. End the line. And we'll go with x and d. All right. All right. Let's just run this now, see what we get. Num primes. Oops. Hyphen lm. All right, let's start at the top here. 4 is divisible by 2. 6 is divisible by 2. 8 is divisible by 2. What was skipped there? 5, 7, the primes, right? So I need to those are the ones I need to count, right? What am I missing anything? 12 is divisible by 2 and it's divisible by 3, right? 14 is divisible by 2. And then why don't we get that it's divisible by 7? Because we've already checked 2 times 7. The square root of 14 is less than 7. That's why we don't need to check it, right? Again, this number line here, this square root of n, we get that 2, and then the 7 is on the other side. We don't have to test for it, right? Okay. All right, so I've got the beginning of a solution here. Help me out. All right. Else, it's not necessarily divisible by d, but it might be divisible by something else. Right? What does it mean if I print it out? X is not prime. It is, what is the other thing? Composite. Right? How do I know that it's prime, though? If I go through this entire inner for loop and, yeah, it never prints anything out. So how do I determine that? Okay. I could, or I could start out with 100, and if I say it's composite, then I could subtract it, right? But then be careful because 12 appears twice. It's divisible by 2 and 3. So I need to account for that too. That seems too much to keep in track in my head. Yeah. Let's set a Boolean. Right? A Boolean flag variable. Bool is prime. We'll initially assume that it is prime, true. Right? If we find out that it's not prime, instead of printing it out, actually I'll keep that comment there. If we find that it's not prime, then what do? Is prime is false. Right? Now after that for loop, we know that it's prime or that it's not prime. If it is prime, then let's go ahead and say num primes. Be consistent about my naming conventions here. Plus plus. Where should I start that out by the way? 0. Okay. And if we ever find that something is prime, we increment it. And then after all this, printf number of primes 1, 2, 2% d. That's going to be my n is %d in the line. So that's n and num primes. All right.
You're going to want the counter inside the first one.
Okay. Good question. Before we run it, why do we want it out here? Yeah, I only ever set it once, right? Now I might end up setting it to multiple times, but I need to go through every single possible divisor in order to determine if it's truly prime or not.
I lost track of that.
Oh, okay. All right. Get that out. So, moment of truth, I should get 25, right? Ah, cool. Let's bump that up before we make some improvements here. And let's ask Wolfram Alpha, how many primes are there between 1 and 1,000? 168. So GCC and 160. Okay, great. I'm convinced. All right. But you know what? I do this over and over and over again. Right? It took a lot there because I had to keep track of the outer for loop that iterates over all. In fact, you saw me mix up n and x there. Right? What could we do to improve this looking ahead to writing functions. What if you had a function instead that was is prime, right? If is prime x. Isn't that much simpler code right there? Right? Well, that just means that we just took that chunk of code that I wrote that we think is correct, that we know is correct, and that we can put it into a function so that we can focus on one thing at a time. Not focus on all of the numbers 1 to 100 or 1 to 1,000 and that it's prime. Just let's focus on one number, whether or not that's prime. Right? Bool is prime. Int x. And that code that I just erased, I can put it here. And let's go A style it. There we go. All right. Is prime. Now let's think about this. Do I need this flag value anymore? The moment that you find that it's not prime, right, you're done. Right? You don't have to go through this this loop anymore, right? We can. Somebody asks, "Here's x. Is it prime or not?" I know that it's not prime. Do I need to check anything else? So we can immediately return false. Down here, if we get through all those possible divisors and none of them divides x, then what we can return? True, that it is prime. By placing this into a function, we've made this a lot more straightforward, right? And we are only focusing on one thing now. You do need documentation on this function. In fact, in C, you do it a little bit differently. Here's a preview of what we're going to start looking at next time, or next week or so. Oh, no, next time. I'm going to put the function definition down here, and up here is what's called a function prototype. So computes, or returns true if the given value, given integer, x is prime, false if it is composite. In fact, that allows me to start thinking about any other corner cases here. For example, a 0. If I did 0 up here, what would end up happening? 0 divided by whatever. Or what about 1? Or whatever, right? I can make some improvements here. If x is less than or equal to 1, right, then I can say that it's not prime. Return false. There are all those corner cases there. Right? Else if x is equal to 2, I could return true. And now that really simplifies my loop. Because what could I do? I don't have to start at 2 anymore. I can start at 3. Do I need to bother checking 4? I could go up by increments of 2 now. 3, 5, 7, that thing that I mentioned at the beginning, that we could simplify it and make it a little bit faster. Just a little bit faster, by the way. This is still going to be exponential. This is not going to be the Sieve of Eratosthenes, this brute force kind of way of doing it, is not at all acceptable. Right? But let's make sure that it still works. What was it again? 168? Oh, now we've broken it. So, true, false. Oh, what did I do wrong? Otherwise it's true. Oh, I broke it somehow. If is prime. Darn it. Anybody else? See what I broke? What did I break? Damn it. All right, let's walk through this. 3, we go up by 2s. It's not prime. Oh. Okay. Not just that it's equal to 2, but if it's divisible by 2. Then I'm getting a whole bunch of even numbers saying that it's they're primes. There we go. I screwed that up. Sorry. No, that's even worse now. Oh, is it true? False. There we go. Now I can separate 2. Else if x is equal to 2, then I can return true. There we go. And otherwise, If it's divisible by 2, I can go ahead and go false. There. Now we're back to 168. Was that correct?
Yes.
168. Good. Let's bump that up to, I don't know, 10,000. And ask Wolfram Alpha, 10,000. GCC this. A dot out. 1229. 1229. All right, we're good. All right. What if I asked, I don't know, 1 million? Is that 1 million? There we go. Oh, okay, it's still fast. Let's go ahead and go with 1 million. 1, 2, 3, 1 billion. So, there we go. While that's running, let's come over here and ask Wolfram Alpha. Can you come up with that answer? Yes, because they probably pre-computed all of these things in one big giant memory table somewhere, and it's all cached. Although it's taking them a while to look up that table, fine. I don't know if that's just the network connection or what, but there we go. Oh, nope. That's too big for you? Come on. It's definitely too big for us. This is going to take weeks, months, years, centuries to actually compute. Right? Why? Because it's exponential. Right? You are doing an exponential amount of work. Right? If I just had n things, and n was 1 billion like it is right now, 1 billion things isn't anything for a computer. But we don't have just 1 billion things. What this is actually doing is some sort of 2 to the n computations. Now tell me about 2 to the 1 billion. Yeah, that's a lot.
More than 1 million.
Yeah, 2 to the, I think like 200 or something like that. That's the number of atoms in the universe. So you're talking about 2 to 1 billion. Right? In fact, it could probably answer that. No results found. Okay. Number of atoms in the universe divided by 12. Okay, so it's not exactly that. What is it? 10 to the 79th. What if you converted that to base 2? Yeah, it'd be about 200, 300 or something like that. But we're doing 1 billion in the exponents. Right? Think it's going to compute in your lifetime?
Maybe.
Yes. Depends on how long you plan to live, but no. Definitely not my lifetime. Right? So we're just going to kill that. It was not an infinite loop. It's just you're doing something astronomical. Right? And being able to recognize that and see, oh no, we should not be doing something like that, it separates just a coder from a computer scientist or computer engineer or software developer or software engineer. Right? Yeah.
Is there a greatest common factor function?
Probably not. Definitely not in C. There's probably not even a GCD function. Greatest common. That's what she said. No, I don't think that there's a GCD. Even a GCD would be 2 numbers, so that's not going to give you any answer on whether or not one number is prime.
So I was just thinking, if you do like the number we want minus, and then the number minus 1, if it's not 1.
There are tricks like that you can use with GCD to cut it down, but not down to polynomial time. There is a primality testing, the AKS algorithm that was discovered, I think, 20 years ago or so, that it does run in polynomial time. Yeah, 20 years or so, so only after 2,000 years of modern mathematics did we finally find a primality test that ran in polynomial time. And I think that this actually ends up being end of the 12th or something. So it's still not the practical way that primality is tested. Instead, if you really want to do primality testing, they have probabilistic algorithms that, with probability 99%, this is a prime, right? And okay, well, if you want 99.9%, you can pay a little bit more for the computation and get it a little bit more, but to get to 100%, you're doing that factor, that kind of work there. Yeah.
Scroll back to the
Sure. Is it wrong? Or? I'll post this code later on if you want to, but All right, so next time we'll talk about functions and how to do them in both languages.